morning, everyone. Thank you for attending. My lecture this morning is about the swarm. How many guys had heard about the cloud? Everyone. IoT, everyone. And about the swarm. Someone had heard about the swarm? So I will talk about the same stuff, but from a different perspective, from a bottom-up perspective, not from a top-down. So basically, I'm talking about a joint project between the University of Berkeley and the University of São Paulo in Brazil. And particularly, we had established a swarm computing lab at the University of São Paulo, and here's the picture of my center. So, the swarm. We have swarms everywhere, inspired by the nature. So in 2008, Professor Jan Rabai, a professor from the University of Berkeley, had proposed his idea. He started to observe that in the edge of the cloud, I mean everywhere, trillions of devices are appearing every day, and the cloud doesn't fix everything. Basically, the cloud is a centralized approach, and we have many barriers when we imagine in a near future integrating trillions of devices. And another thing that is really important, there is a lot of computing resources available in the edge, and we are not exploring them. They are just there. In recent years, we are very biased on the cloud, but we're forgetting that there is a lot of resources scattered around, and we're not exploiting them. So the swarm approach tried to fix this problem. So as I mentioned before, current IoT approaches are quite centralized, and that leads us to several scalability barriers. Usually when we centralize things, we cannot control everything at the same time. Imagine how ants organize themselves, or the ant farm, or bees on the hive. At the same time, there is a lot of computing resources, memory, processing, storage. Take a look in the last 96 boards that we are developing in this community, and imagine when we multiply these 96 boards by millions or maybe more boards. Imagine the amount of computing resources, memory, storage, network available, and the cloud doesn't answer for that. So our main goal in the long term is building a framework for collective, organic intelligence. What means organic? We can imagine that all these devices together, they can somehow swarm like insects, and eventually, on an organic way, they can do or perform complex tasks. That is our final goal. We can see that in nature. Animals, they swarm themselves to protect themselves against a predator. For example, we can swarm our devices to protect us against hackers, to protect us towards our privacy. So, inspired on that, we group a number of very smart professors, engineers, and students, and we are trying to understand how the swarm, where we have these cooperating nodes scattered in the whole infrastructure, they can help human life. So our vision is that we can have swarm computing behavior on transit, on public infrastructure, and even more. So our approach is really inspired in communities of living agents that can somehow swarm. So the idea is that insects are very simple from the intelligent point of view, and also they have very limited resources. If you take a look on a single ant, they had very limited intelligence, force, energy, and communication, but together they do marvelous things. So that is the idea behind when we design an insect. That's a way to see the IoT. So our focus is to make these devices or these insects more intelligent. And then, eventually, they can perform complex tasks on an organic way. So when we mention organic, we want to have a systematic coordination of parts. So in the end, they can behave as an organism. So we are designing the Swarm OS, the Swarm operating system. So this operating system needs to have the following features. Need to be interoperable, need to support somehow a microeconomy. That's something very interesting too. The business model of the cloud is very self-established, but we still need to find different and novel approaches in terms of the swarm economy. And since we are talking about trillions of devices, our approach is again a bottom-up approach. So we believe on a microeconomy of devices sharing the resources between them, keeping some traditional concepts like the quality of service and a rewarding mechanism. So eventually, in future, I have my smartphone here with some memory, and then someone else needs memory. So eventually, our devices can share these resources amongst them. Of course, we need to think about security and privacy. And finally, what we call scope, or maybe the global discovery. So insects, they need to know their positioning, their ownership, and their priorities. So in terms of interoperability, our approach is what we call a semantic mediation service. In microeconomy, as I mentioned before, we are focusing on the quality of service and a rewarding mechanism. And in security, it's also related to semantics, but also we had the problem of performance, because nowadays, most of the security infrastructure available is quite expensive when we consider very simple IoTs, and they need to be also real-time. So some of these solutions are still very open. And finally, in terms of scope or global discovery, we want to give a multi-level approach where a given insect can understand its geography. For example, my 96 board can understand that it is in Brazil. It can have a relative positioning. For example, my device could be 20 meters from me. And finally, the semantics. Okay, my device is under my refrigerator. And again, we are looking to a microservice approach. So we are trying to decompose everything on a very small grains. So how we are making that viable? The responsibility of USP in this partnership with UC Berkeley, we are responsible for the broker. The broker is the software piece that do the mediation amongst all devices. So the broker is distributed, heterogeneous, and language agnostic. So in the end, we want to port the broker to virtually any device. And all these Swarm OS features are being implemented in the broker. Considering that, we are considering the 96 boards our target to port the broker. Until now, I had collected something like 296 boards on a very heterogeneous way. We have bubble guns, we have high keys, we have Dragon boards, we have also some Raspberry Pis, we have some LeMaker high keys, LeMaker's guitars. So we want to deploy our operating system considering a very diverse and heterogeneous environment. And we had considered the 96 boards as our main target. So everything is going very well. By the third quarter of 2017, we hope to have the first stable version of our Swarm OS, that again, our focus is the broker. And finally, I want to emphasize that the Swarm is a novel and a complementary approach for IoT. It's quite well suited for high-performance scalable IoTs in the edge. That's why we consider the 96 boards our main target. And at this moment, we are discussing some deployments and some demonstrations. So we are targeting home automation, traffic safety, solar energy management, and finally, water leakage management. I live on a very big city, 19 million people, and water management and water leakage is a key issue in these big cities. So the water department of our city is considering to use a Swarm approach to manage water leakage in that big city. So in here, we have some publications. I should also include some publications, and I see some people take pictures. A very nice reference is the seminal paper of Professor Ian Rabai from 2008. And I am available for questions and discussion. Thank you very much. Any question? Oh, yeah. That is a very important question because it's a different kind of operating system because we should consider the legacy. So the idea is not reinventing the wheel, creating a new kind of operating system. So the current deployment that we have, it's a kind of wrapper. So it's a small piece of software that could be operating system agnostic and language agnostic. And this operating system can be, this wrapper can be easily deployed in any heterogeneous platform. So in purpose, we are not trying to homogenize our 96 board and farm. I mean, we want to have different boards with different capacities and different operating systems. And then we try to inject this little piece of software. So after that, devices can behave like insects. So when we talk about a new operating system approach, we should consider the legacy. So at this moment, it's a wrapper, and there is a discussion in my team about embedding that as a daemon inside the operating system. But that is quite relevant to the success of this initiative. We usually people think about languages like Java. We decide to do a radical shift to modern languages. So in our case, we are using a new language named Elixir that facilitates the semantic representation of the swarm. Thank you for the question. Any another question?
How rugged do you find these boards are?
How?
How rugged, as in you're talking about deploying them outside?
Oh, yeah. So that is another problem. We are trying to qualify the 96 boards. At this moment, we have a deployment. We have a solar energy using generator on a park nearby. We have 4,000 panels there. So we want to have one insect per panel. We're talking about 4,000 boards. So we have some challenges regarding qualifying the 96 boards to this local environment, but that is about certification. So we are submitting these boards to weather, to environmental life, and then we are trying to design boxes to keep them more safe. But that's also a problem that we doesn't see too complicated, because 96 boards is a step ahead traditional single board computers like Raspberry Pis, and they are more reliable and robust. And that somehow the standards prepare these boards for certification. For example, when you think about solar, you need to consider the environmental temperature. Eventually you can have temperatures higher than 85 degrees Celsius. And the 96 boards are behaving quite well in this scenario. And another question? Well, I will be here. Oh, another question. Yeah. Oh, yeah. It's a framework in the sense that we are specifying the operating system. I mean, we have a lot of software being deployed. Well, when you try to put all pieces together, you need to use all these sort of technologies. You know, you use JSON, Hydra, everything. But we doesn't want to have a framework in the sense where people, we need to focus in the computing model, that is the swarm. The framework, it will be more related when we will address the semantic part, the artificial intelligence injected in the insects. And that is the key part that eventually you need to have a framework, because for every given complex task to be performed, you need to have a different programming approaches. So that is the open part. Everything else will be a kind of piece of software that you inject on an insect, and then they will behave like swarms. For example, discovery services, security services, they are all part of the same infrastructure. You know? We doesn't need to give users programmability openness on this. So most of these things will be clear as soon as we will deploy the first implementation, probably in the third quarter of this semester. Okay. Hi, John. Oh, yeah. Our center is really committed with this swarm approach. And we'll talk about collaboration opportunities. The swarm is a big initiative in Berkeley and also in Brazil. Many companies like Qualcomm, Google are supporting this initiative there. And we are looking for several dimensions of these program. For example, on Friday, we'll talk about an open GPU that we're designing. The GPUs are becoming an important part in terms of processing of these devices. So on a given point, when you use the swarm approach, suddenly the IoTs became relevant And then you need to look for high performance in the edge. So when you talk about high performance in the edge, you need flops, and you need processing capacity. And we understand that ARM is doing very well in terms of processing capacity. We are achieving almost teraflop computing in some of these devices. But the GPU is the important part. And GPU consumes a lot of energy. And if you see insects, doesn't consume a lot of energy. So one talk that we'll give on Friday is about this functional open GPU that we're designing. And the second part is about collaboration. We have manufacturing facilities. We can manufacture something like 4,000 insects per day. In fact, we're trying to ramp up a program on this. And I hope that you'll be here on Friday to foster this discussion. And I will be here the whole day. In purpose, I have much more presentations about the software parts, but I decide to preserve and avoid it. But you see here that I have all pieces of the operating system. I have a given specific presentation. I will be very happy to discuss this more technically after this talk. Could be a little bit boring, discussing discovery methods or how to scale 200,000 devices on a water deployment on a big city like São Paulo. And another question? Okay. Yes.
So is it going to be cost effective to deploy 196 volts per panel?
Well, that's one plan. We want to have 196 board per panel. And my students are designing a shield for that. So we're talking to something like 4,000 boards. And since we can manufacture them, we can reduce significantly the cost for 1/3 of it. So it's quite interesting. We have a lot of problems, including ad hoc, self-configurable networks, Most of the networks available doesn't support more than 256 devices. So we are designing some fully distributed networking schemes to self-configure 4,000 devices, Because that is the beauty of the swarm. You doesn't have a centralized approach. It's like ants, You just drop the ants, and sometime later, the ants will start to build the ant farm. So we want to drop 4,000 boards and make these boards self-configure and organize themselves without human intervention. That is quite, it's a different mindset, It's a different way to see things, Where you doesn't have a centralized and again, bureaucratic approach. Okay? So I think my time goes. Thank you very much.